If the electrons flowing in a circuit move backwards and forwards about a mean position, then the current produced is known as alternating current, or AC. In this lesson, we will review the operation of a simple alternator or AC generator. We will look at the advantages that AC systems have over DC systems, and we will explain the terminology that you need to become familiar with when discussing AC systems. A simple AC generator consists of a loop of wire or an armature rotating in a magnetic field. We will take a look at the simple generator as the armature rotates through 360 degrees to see what sort of voltage is produced. In the position shown here, the coil will initially be moving in parallel with the magnetic field, with a phase angle of 0 degrees, so no EMF will be induced. As the coil continues to rotate, it begins cutting the field at a small but increasing angle, and an EMF begins to be induced. As the coil approaches 90 degrees to the direction of the magnetic field, the maximum number of lines of flux are being intersected, and the EMF is at its maximum. Between 90 and 180 degrees, the number of lines of flux being cut by the coil reduces again, so the EMF reduces, until at the 180 degree point, the coil is again moving in parallel with the magnetic field, so no EMF is being induced. As the coil moves around from the 180 degree point, it once again begins cutting through the field lines, but now in the opposite direction, so an increasing EMF is induced with an opposite polarity, until at the 270 degree point, the coil is cutting through the maximum number of flux lines, and the negative EMF is at a maximum. The EMF now begins to fall again until the circle is completed. The coil is again moving parallel to the field, the EMF is 0, and the cycle begins again. The alternating voltage produced by this type of generator is known as a sine wave or a sinusoidal output. A sine wave can be given an angular notation called phase. One cycle represents from 0 to 360 degrees of phase. The current flowing in the external circuit will be an alternating current, or AC. That is to say, the current will first flow one way, then change direction and flow the opposite way as the polarity of the induced EMF changes. There are several terms used to describe alternating current, and you need to become familiar with these terms. As shown on the graph, a cycle is one complete series of values. A cycle can be split into two halves, known as a positive half cycle and a negative half cycle. We have already mentioned phase angle or phase, and we know that one cycle represents from 0 to 360 degrees of phase. The number of cycles occurring in each second is the frequency of an alternating current. The unit of frequency is the hertz. 1 cycle per second is equal to 1 hertz. Aircraft constant frequency AC supply systems usually have a frequency of 400 hertz. The period is the time it takes for one cycle to occur. It is the reciprocal of the frequency. The period in seconds equals 1 over the frequency. The amplitude or peak value is the maximum value attained in one cycle. Alternating current or AC electrical power has a number of advantages over direct current or DC. Some of these advantages are self-evident, but others will become clear as you move further into the subject. AC generators are simpler and more robust in construction than DC machines, because they do not have commutators, and only the light current field coil is rotating. Because they don't have commutators, AC generators do not suffer from the problems of arcing at the commutator associated with DC machines, and consequently are more reliable, especially at high altitude. They also require less maintenance. An AC generator can be significantly lighter than a DC generator, with the same power output. Because the rotating elements are much lighter, AC generators can be operated at much higher rotational speeds than DC generators, so they can produce a much higher voltage output. Three-phase AC motors, which again do not require commutators, are simpler, more robust, and more efficient than DC motors. Again, AC motors are fully explained in a future lesson. The supply voltage can be converted to a higher or lower value with almost 100% efficiency using transformers. Any required DC voltage can be obtained simply and efficiently using transformer rectifier units, or TRUs. Transformers and TRUs are fully explained in future lessons. AC generators operate at much higher voltages than DC machines, so for the same amount of power, the current required is proportionally less. This means that considerably thinner and lighter cables can be used than is possible in DC systems. Spend a moment studying the list on the screen before moving on. Because they don't need commutators, practical AC generators normally have the positions of the field and the armature transposed from the positions used in DC generators. That is to say, the field is on the rotating assembly, and the high-power armature windings are stationary, in the same way that they are on a DC alternator, but without the rectifier. The field may have more than one pair of magnetic poles. Shown here is a generator with 3 pairs of poles. Aircraft AC generators normally have 6 or 8 poles. A cycle is completed each time a north and a south pole of the magnetic field move past the armature. Thus, the frequency of an AC generator is the number of times a north and a south pole pass the armature in 1 second. The formula for calculating the frequency in hertz of an AC generator is shown on the screen. For example, a 6-pole generator rotating at 8,000 RPM will have an output frequency of 6 divided by 2 multiplied by 8,000 divided by 60, which is 400 Hz. We can see from this that the frequency of an AC generator is dependent on the rotational speed of the rotor and the number of poles in the field. The effective value of an alternating current is calculated by comparing it with direct current. The comparison is based on the amount of heat produced by each current under identical conditions. An AC current with a peak value of 10 amps will be constantly varying between 0 and 10 amps. So a steady DC current of 10 amps will make a resistor hotter than will the AC current with a peak of 10 amps. To make the resistor as hot with an AC current, its peak value must be higher, so that its mean value can be 10 amps. This mean value is termed the root mean square, or RMS value. As the current or voltage rises from 0 to maximum in 90 degrees of phase angle, the mean value will occur at the midway point of 45 degrees. As the values follow a sine curve, then the value at 45 degrees can be calculated using the formula sine equals opposite divided by hypotenuse. In our case, the hypotenuse is equal to the peak value, and the opposite is equal to the mean value. the sine of 45 degrees is 0.707. So in our case, 0.707 equals the mean value divided by the peak value. By transforming the formula, we can say that the mean or RMS value of alternating current or voltage with a sinusoidal waveform is given by the formula RMS equals 0.707 multiplied by the peak value. In our earlier example, the AC with a peak value of 10 amps has an RMS value of 10 multiplied by 0.707, or 7.07 amps, which explains why it produces less heat than the 10 amp DC current. Most AC supply values are given in RMS terms. Ammeters and voltmeters measuring AC are normally calibrated in RMS values. That is the end of the lesson. You now know the advantages that AC electrical systems have over DC systems. They are being displayed on the screen. Spend a moment reviewing them before moving on. You now know the terms that are used when describing alternating current. They are being displayed on the screen for you to review. Finally, you can calculate the output frequency of an AC generator using the formula shown. In this lesson, we will discuss the effects that resistance, inductance, and capacitance have on voltage and current in an AC circuit. Current and voltage in an AC circuit have the same frequency, and their waveforms or the shapes of their cycles are the same. In aircraft AC generator systems, the voltage and the current waveforms are both sinusoidal. In a DC circuit, the current flow is directly affected by the applied voltage and circuit resistance in the relationship formulated by Ohm's law, I equals V divided by R. That is to say, the current is directly proportional to the voltage and inversely proportional to the resistance. There are very few AC circuits in which the current is affected solely by the applied voltage and resistance. In most AC circuits, because of the ever-changing values of voltage and current, the current flow is influenced by the magnetic and electrostatic effects of inductance and capacitance. There is no such thing as a pure resistance when considering an AC circuit. All resistors, even a simple piece of wire, have a property known as inductance as well as resistance. However, for the purpose of studying AC theory, we will assume that we can build separate circuits having only resistance, inductance, or capacitance. We will look at the effects that each of these three properties individually has on the voltage and current in an AC circuit. Beginning with resistance. In a theoretical AC circuit containing only resistance, both the current and the voltage pass through zero and reach their peaks in the same direction simultaneously. In such circuits, the voltage and current are said to be in phase. You will recall that by moving a conductor relative to a magnetic field, or vice versa, a voltage is induced in the conductor. You will also recall that the voltage is only induced when the conductor is cutting through the lines of magnetic flux. You also know that when a current is flowing in a conductor, a magnetic field proportional to the magnitude of the current flow is formed around the conductor, and that by winding the conductor in the form of a coil, a magnetic field with lines of flux similar to that of a bar magnet, is formed, and the strength of the magnetic field is increased. Movement of the flux around a coil can be achieved without physical motion, by varying the current flow, thereby causing the lines of flux around the coil to expand or contract. We can use this fact to induce a voltage in an adjacent coil. To demonstrate this, we place two coils close together, with one known as the primary coil connected to a DC power supply via a switch, and the other secondary coil connected through a load to a center zero ammeter. With the switch open, there will be no current flowing, so there will be no magnetic field around the primary coil. When the switch is closed, current will begin to flow, and a magnetic field will build around the primary coil. As this field expands out from the coil, it will cut through the turns of the secondary coil, inducing a voltage in it, causing a current to flow. Once the current flow in the primary circuit stabilizes, the magnetic field will also stabilize. The lines of flux will have no movement relative to the secondary coil, and the induced current will fall to zero. When the switch is opened, the current flow in the primary coil will fall to zero, and its magnetic field will collapse. The lines of flux of the collapsing field will now again be cutting through the secondary coil, but this time in the opposite direction, and a voltage and current in the opposite sense will be induced. Once the magnetic field has completely collapsed, the relative movement will again stop, and the induced current will again fall to zero. If we now change the supply to the primary coil from DC to AC, then with an ever-changing and alternating current flow in the primary circuit, its magnetic field will be constantly expanding and contracting. Therefore, there will be a continually induced voltage and current flow in the secondary coil, proportional to the primary coil AC waveform. This is called mutual induction, and is the principle of operation of transformers. If we remove the secondary coil, the AC supply to the primary coil still generates an ever-changing magnetic field, which, as it cuts through the wires of the coil, has the effect of inducing a voltage in the primary coil itself. This is called self-induction, and according to Lenz's law, the voltage induced will oppose the change of current in the circuit. This self-induced voltage is often referred to as the back EMF, or reactance. The ability of a coil to produce a back EMF is known as inductance. There are a number of factors which can affect the magnitude of the induced voltage or back EMF. The more turns of wire there are in the coil, the stronger will be its magnetic field, producing a larger back EMF. Placing a soft iron core inside the coil will produce a stronger magnetic field, with a consequent increase in back EMF. If the frequency of the supply is increased, the rate of change of current will increase, causing an increase in the rate of change of the magnetic field, and again an increase in the back EMF. The effect of inductance in an AC circuit is to cause the voltage and current to be out of phase. Because the back EMF opposes the current flow, the current lags the voltage. In a circuit having only inductance, the current lags the voltage by 90 degrees of phase. Any device having inductance can be referred to as an inductor. The unit of inductance is the Henry, and its symbol is a capital L. A circuit has an inductance of 1 Henry if a current change of 1 amp per second induces a back EMF of 1 volt. Inductance is usually expressed in millihenries or microhenries, as the Henry is too large a unit for practical use. 1 millihenry is 1/1000th of a Henry, and 1 microhenry is 1 millionth of a Henry. Capacitance is the ability of a circuit to store an electrical charge. A device used to introduce capacitance into a circuit is known as a capacitor. Capacitors are fully explained in the DC series of lessons. You will recall that a capacitor consists of two plates separated by a dielectric, which can be, amongst other things, air, mica, or waxed paper. Three factors affect the amount of charge a capacitor can hold. They are the area of the plates, the distance between the plates, and the type of dielectric used. The capacitor will store an electric charge, much like a hydraulic accumulator stores fluid under pressure. But first, it needs to be charged. When connected to a DC power supply, electrons will be removed from the plate connected to the positive terminal and added to the plate connected to the negative terminal. Conventional current flow will be from positive to negative. This process will continue until the plates become saturated, when no more current will flow. The potential difference between the plates is at its maximum, and the capacitor is now fully charged, its voltage being equal to the input voltage. If the capacitor is now removed from the supply, it will retain this charge until it is connected to an external circuit, when the surplus electrons on one plate will flow through to replace the shortfall on the other. Notice that the capacitor has discharged in the opposite direction to which it was charged. Remember that electrons do not pass between the plates through the dielectric. When fitted in an AC circuit, a capacitor will be constantly charging and discharging, as the applied voltage is constantly reversing polarity. As the applied voltage falls, the capacitor discharges current back into the circuit. This has the effect of shifting the voltage out of phase with the current, and in a purely capacitive circuit, the current will lead the voltage by 90 degrees. The unit of capacitance is the farad, F. In terms of capacitance, the farad is a very large unit. 1 farad capacitor could be as large as a soft drink can. The farad is therefore subdivided into smaller, more convenient units. 1 microfarad is 1/millionth of a farad. 1 nanofarad is 1,000th of a millionth of a farad. And 1 picofarad is 1/millionth of a millionth of a farad. Capacitors are also rated by their working voltage. This is the largest DC or peak AC voltage which can be applied across the capacitor. It is usually marked on the case of the capacitor, and if it is exceeded, the dielectric may break down, permanently damaging the capacitor. A useful mnemonic for remembering the relationship between voltage and current in inductive and capacitive circuits is the word civil, where C stands for capacitance, I for current, V for voltage, I for current, and L for inductance. So in a capacitive circuit, current leads voltage, and voltage leads current in an inductive circuit. That is the end of the lesson. Here is a summary of the most important points. In aircraft AC generator systems, the voltage and the current waveforms are both sinusoidal. In a theoretical AC circuit containing only resistance, the voltage and current are in phase with each other. The unit of inductance is the Henry. The symbol for inductance is a capital L. In an AC circuit having only inductance, the current lags the voltage by 90 degrees of phase. The unit of capacitance is the farad. In an AC circuit having only capacitance, the current leads the voltage by 90 degrees of phase. In this lesson, we will look at the forces that oppose current flow in AC circuits, and we will examine the relationship between these forces. We will start by looking at theoretical circuits containing, in isolation, resistance, inductance, and capacitance. Beginning with resistance. In a theoretical AC circuit containing only resistance, the voltage and current are in phase, and Ohm's law applies. Resistance can therefore be calculated using the formula R equals V divided by I. The opposition to current flow in a circuit containing inductance is called inductive reactance. It is called reactance rather than resistance because it varies with the frequency of the supply, as well as the value of the inductance. Inductive reactance is measured in ohms and is given the symbol XL. To determine inductive reactance, the formula XL equals 2 pi FL is used, where pi is a constant, F is the frequency, and L is the inductance in henries. The formula itself is of little importance, but we can see from it that for a fixed value of inductance, the inductive reactance will increase if the frequency of the supply voltage is increased. This will lead to a decrease in the current flow in the circuit. Conversely, and more importantly, if the circuit frequency decreases, the inductive reactance decreases, and the circuit current increases. The opposition to current flow in a circuit containing capacitance is called capacitive reactance. As in the inductive circuit, the amount of reactance is dependent upon frequency and the capacitance in farads. Capacitive reactance is measured in ohms and is given the symbol XC. It can be calculated by using the formula XC equals 1 over 2 pi FC. Again, the formula itself is not of any great importance. However, from the formula, it can be seen that as frequency increases, capacitive reactance decreases, so the circuit current will increase. Conversely, if frequency decreases, capacitive reactance increases, and circuit current will decrease. The total opposition to current flow in an AC circuit is a combination of resistance, inductive reactance, and capacitive reactance. It is known as impedance. It is measured in ohms and given the symbol Z. Because of the differing phase relationships between the voltage and current in inductive, capacitive, and resistive components, inductive reactance, capacitive reactance, and resistance cannot simply be added together. Inductive reactance can be thought of as having the opposite effect to capacitive reactance, as one effect causes the current to lag the voltage by 90 degrees, and the other the current to lead the voltage by 90 degrees. So their effects on current flow are 180 degrees apart. Total reactance can be found by subtracting the smaller from the larger. The current flow in a resistive circuit is in phase with the voltage, so resistance is out of phase with the total reactance by 90 degrees. Impedance is the vector sum of resistance and total reactance. Because the resistance is 90 degrees out of phase with the total reactance, we can use Pythagoras' theorem to calculate the impedance. The formula for calculating impedance is being displayed on the screen. Changes of supply frequency in a circuit will have the opposite effect on capacitive and inductive reactance. The manner in which the inductance and capacitance react in an opposite way to changes of supply frequency means that there will be one specific frequency for each circuit at which their reactances will be equal. When the capacitive and inductive reactances in a circuit are equal, the circuit is said to be resonant. The frequency at which this occurs is known as the circuit's resonant frequency. Radio tuners often use resonant circuits for their operation. That is the end of the lesson. Here are the main points that you'll need to take from it. Reactance, measured in ohms, is the opposition to current flow produced by inductors and capacitors. For a fixed value of inductance, the inductive reactance will increase if the frequency of the supply voltage is increased. This will lead to a decrease in the current flow in the circuit. Inductive reactance will decrease if the frequency of the supply voltage is decreased. This will lead to an increase in the current flow in the circuit. For a fixed value of capacitance, the capacitive reactance will increase if the frequency of the supply voltage is decreased. This will lead to a decrease in the current flow in the circuit. Capacitive reactance will decrease if the frequency of the supply voltage is increased. This will lead to an increase in the current flow in the circuit. Impedance, measured in ohms, is the vector sum of resistance and total reactance. When the capacitive and inductive reactances in a circuit are equal, the circuit is said to be resonant. The frequency at which this occurs is known as the circuit's resonant frequency. In this lesson, we will look at power in AC circuits. We know that the power absorbed in a DC circuit is the product of the voltage and the current. Due to the change in phase relationship between voltage and current in AC circuits containing inductance and/or capacitance, the actual power absorbed is not necessarily the same as the power apparently supplied. To see the effects of resistance, inductance, and capacitance on power, we will examine them separately. And then we will look at a practical circuit having a combination of all three. In a purely resistive AC circuit, the instantaneous power value is found by multiplying the instantaneous values of current and voltage. If this process is carried out over a full cycle, it will give the power waveform shown on the screen. You will notice that the power waveform is always positive. This is because the voltage and current are in phase. So in the negative half cycle, both the voltage and the current are negative, and two negatives multiplied together produce a positive. The frequency of the power waveform is twice that of the voltage and current. The average value of this power is known as the true power, real power, or wattful power, and it is the product of the root mean squared current and voltage. It is measured in watts or kilowatts, and it represents the work being done to rotate the generator. Here we see a purely inductive circuit, where the current lags the voltage by 90 degrees. As in the resistive circuit, by plotting instantaneous values of current multiplied by voltage, we can obtain the waveform of instantaneous power. Again, the frequency of the power waveform is double that of the voltage and current. However, this time half of the wave is positive and half negative. This is because whenever the voltage and current are on opposite sides of zero, we have a positive multiplied by a negative, which gives a negative. The positive areas represent power given to the circuit to generate the magnetic field, and the negative, power returned by the back EMF. Power produced in this way is called reactive power, and is the product of a voltage and current which are 90 degrees out of phase. The units of reactive power are volt-amps reactive, or, for higher amounts, kilovolt-amps reactive. In a circuit that contains only inductance, the positive and negative portions of power cancel each other out, and the true power is zero. Power in a purely capacitive circuit is very similar to that in an inductive circuit, because the current is also out of phase with the voltage. But this time the current leads the voltage by 90 degrees. Once again, the positive power is equal to the negative power. Thus no true power is absorbed. The circuit power is again all reactive power. A practical AC circuit will always have some resistance and some inductance. The amounts of each will depend on the construction of that circuit. The circuit may also have capacitance if capacitors are fitted. All AC circuits therefore have both resistance and reactance. These will produce true and reactive power respectively. The total power being felt in the circuit will be the vector sum of the true power and the reactive power. This power is known as apparent power. It is also sometimes referred to as theoretical power or rated power. Irrespective of their phase relationship, apparent power can be calculated by multiplying the RMS voltage by the RMS current. It is measured in voltamps or kilovoltamps. We can use a similar vector diagram to the one that we use to calculate impedance to work out a circuit's apparent power. In the power vector diagram, we have true power along the baseline, and since in a reactive circuit the current is 90 degrees out of phase with the voltage, we have reactive power at 90 degrees to it. As we said, the apparent power in the circuit is the vector sum of the true and reactive powers. The phase angle, which is the angle by which the current leads or lags the voltage, is the angle between the true and apparent power lines. The relationship between true and apparent power is an important one. It is expressed as a power factor, or PF. The power factor is the true power divided by the apparent power. As you can see from the vector diagram, this is the cosine of the phase angle. In a theoretical purely resistive circuit, the phase angle is 0 degrees. The true power is equal to the apparent power, so the power factor is 1. This is good, as all of the power in the circuit is being used to do useful work. In a purely reactive circuit, the phase angle is 90 degrees, the power factor is 0, and no useful work is being done. Circuit designers attempt to maintain the power factor as close to 1 as possible. That is the end of the lesson. Here is a summary of the main points. The power used to overcome resistance is known as real power, true power, or wattful power. It is measured in watts or kilowatts. It represents the work being done to drive the shaft of the generator. Power produced in a purely inductive and/or capacitive circuit is known as reactive power. It is measured in voltamps reactive or kilovoltamps reactive. The total power being felt in a circuit containing both resistance and reactance is the vector sum of the real and reactive power, and is known as apparent power. It is measured in voltamps or kilovoltamps. The power factor is the true power divided by the apparent power, or the cosine of the phase angle. In a purely resistive circuit, the phase angle is 0 degrees, the true power is equal to the apparent power, and the power factor is 1. In a purely reactive circuit, the phase angle is 90 degrees, and the power factor is 0. Most modern aircraft use alternating current, or AC, in their primary electrical systems. The AC is supplied by an alternator or alternators. Alternators are often referred to as AC generators, and this is the name that we will use. We will begin this lesson by reviewing the operation of a simple AC generator. We will then go on to look at polyphase or multiphase AC generation. In a DC generator, the rotating part is always the armature. In an AC generator, this is not necessarily true. There are two types of AC generator. They are the rotating armature type and the rotating field type. The rotating armature AC generator is similar in construction to a DC generator in that the armature rotates in a stationary magnetic field. As it does so, an EMF is induced into it, and this EMF, rather than being converted to DC, as it is in the commutator of a DC machine, is taken from the rotating assembly as AC through slip rings. Rotating armature AC generators suffer from a number of disadvantages. The rotating coils are heavy and centrifugal forces are high. Efficient insulation of the rotating coils is difficult. The resistance across the brushes to the slip rings is high. And the rotating armature coils are difficult to cool. For these reasons, the rotating armature is only used in very small output AC generators and is not generally used for supplying aircraft AC systems. Most AC generators are designed with a rotating field and a stationary armature, in the same way that DC alternators are constructed, but without the rectifier. The rotating part of the generator is known as the rotor, and the stationary part the stator. The field can be energized either by a permanent magnet or by DC from a separate source. One advantage of a rotating field AC generator is that only a low current is fed through slip rings to the field windings. The output is taken from the stationary armature windings, which means that problems associated with arcing from the brush gear are greatly reduced. The stator windings or coils are directly opposite each other and are connected in series to supply the output. The rotor consists of two poles of opposite polarity. The maximum output current from an AC generator depends on the amount of heat which can be absorbed by the armature. The armature windings, in common with all conductors, have some resistance. The power lost in the armature is this resistance multiplied by the armature current squared. This power loss heats up the conductors and can, in extreme cases, destroy the insulation of the windings. For this reason, AC generators are rated in terms of this armature current as well as by their voltage output. Thus, every AC generator is rated in voltamps or kilovoltamps. You will recall that this is the apparent power being felt by the armature. Polyphase or multi-phase AC generators have two or more sets of single-phase armature windings, commonly known as phases, symmetrically spaced around the stator. The most common polyphase AC generator has three sets of armature windings. It is known as a three-phase generator and has become the standard AC generation system for aircraft. The phase windings are named A, B, and C. They are mechanically arranged to be at 120 degrees to each other, in the sequence A, B, C. The currents and voltages generated in this type of machine will have the same frequency, but be out of phase with each other by 120 degrees. It can be seen that A phase reaches a peak going positive 120 degrees before B phase reaches a peak going positive. B phase, in turn, peaks 120 degrees before C phase reaches a peak going positive. This gives the phase sequence ABC. The peak values of the voltages induced in the three single-phase windings of the three-phase alternator are therefore 120 degrees displaced from each other. The three phases are independent of each other. A system using three-phase generators has a number of advantages over a system using single-phase machines. Because the generators are effectively three single-phase generators on the same shaft, they have a greater power-to-weight ratio. Three-phase AC motors are very simple and efficient, and for reasons beyond the scope of this course, three-phase generators are easier to connect in parallel than single-phase devices. Although we have said that the three phases are independent of each other, it is normal to connect their outputs together. The outputs can be connected by either the star or delta method. A star-connected three-phase AC generator has the three phases joined at one end to form a connection known as the neutral point. The connections at the opposite end of the phase windings from the neutral are called the line connections. The neutral point is normally grounded and used as the earth return in modern aircraft. It will carry any out-of-balance current between the phase loads. A voltmeter, measuring the potential difference between the neutral and a line lead, would read the individual phase voltage. The potential difference between two line connections is known as the line voltage. In this type of AC generator, the phase voltage and line voltage are different. Because phase voltage is measured across one phase, whereas line voltage is measured across two phases and is the vector sum of the two. The line voltage in a three-phase system can be found by multiplying the phase voltage by the square root of 3, or 1.73. The phase voltage of a typical aircraft supply system would be 115 volts. So from the formula, we can work out that the line voltage is 115 multiplied by root 3, which is approximately 200 volts. The frequency used on aircraft is normally 400 Hz, so a modern aircraft power supply would be 115/200 volts, 400 Hz, three-phase. The Greek letter phi is often used to represent phase. While the voltages of line and phase differ in the star-connected system, because the windings form only one path for current flow between phases, the current flowing in the lines will be the same as the current flowing in the phase windings. Thus line current equals phase current. In a delta-connected AC generator, the ends of the three phases are joined together to form a closed mesh, and the loads are connected in a similar fashion. Because the potential measured across the phase is measured between two lines, the line voltage and the phase voltage are the same. However, because of the way the phases are connected, the line current will always be shared between the phases. And in this case, the line current will be √3 times the phase current. This type of connection is not normally used in aircraft electrical power systems, because it cannot cope with unbalanced loads, as there is no neutral point. However, it may be used for rotational speed sensing equipment, such as in engine RPM indicating systems. That is the end of the lesson. Here are the main points that you should take from it. Most aircraft AC generators have their field windings on the rotor and their armature windings on the stator. AC generators are rated in voltamps or kilovoltamps. Aircraft AC generators are usually 115/200 volt, 400 Hz, three-phase star-connected machines. The three phases are separated by 120 degrees. In a star-connected generator, the line voltage is equal to √3 or 1.73 times the phase voltage. The line current is the same as the phase current. In a delta-connected machine, the line voltage is the phase voltage, but the line current is √3 times the phase current. We know that rotating field alternators, or AC generators, where the field is on the rotor and the output windings form the stator, make up the majority of AC generators in use. There are two types of rotating field AC generator in common use on aircraft. They are brushed AC generators and brushless AC generators. In this lesson, we will look at these two types of AC generator, and we will also examine the various methods used to control frequency in AC generation systems. We will begin by looking at brushed AC generators. The simplest AC generator system is the brushed alternator type. The AC generator itself consists of a rotating field, which is supplied with DC by slip rings and brushes, and a stationary armature, on which are mounted the output windings. In aircraft systems, the output of an AC generator will normally have three phases, but for clarity, we only show one phase here. Control of the field excitation current is by the voltage regulator, which samples the generator output and adjusts the excitation current to maintain the correct output voltage, irrespective of the alternator speed and loads. The voltage regulator in its simplest form is a variable resistance, possibly a carbon pile, connected in series with the field coil. The principle of the carbon pile regulator is fully explained in the DC series of lessons. Most modern voltage regulators are electronic devices with no moving parts. The current supply for the excitation of the rotating field is provided initially from the aircraft's DC busbar. This busbar is powered by the battery until the generator is online, so the initial excitation current is supplied by the battery. Once the generator is online, the AC output is fed directly to the voltage regulator, where it is rectified before being used in the field circuit. A brushless AC generator consists of two generators. The main generator with a rotating field and an exciter generator with a rotating armature on the same shaft. The purpose of the exciter generator is to provide a current for the main generator rotating field, without the need for slip rings and brushes. Also rotating on the shaft is a rectifier unit. The rotating rectifier converts the AC produced in the exciter armature to DC for the main rotor field. The rectifier unit will normally be a bridge rectifier containing 4 diodes. Rectifiers are fully explained in another lesson. As in the brush generator system, the voltage regulator samples the main generator output. But in this system, it controls the exciter generator field strength and thereby its output through the rotating rectifier to the main generator field coils. On initial startup, a brushless generator may be self-excited by residual magnetism in the poles of the exciter generator field windings. Or, if the exciter generator field has no residual magnetism, it will be excited by externally supplied DC, possibly from the battery. Because, as their name implies, brushless AC generators have no brushes, they are more reliable than brushed AC generators. And they can also have a higher power-to-weight ratio. Modern brushless AC generators may have a third generator on the same shaft, called a permanent magnet generator, or PMG. This generator provides the excitation current for the exciter generator. The PMG consists of a rotating permanent magnet, which induces a current in its stationary armature windings. The output from the PMG is rectified and fed via the voltage regulator to the stationary field windings of the excitation generator. Irrespective of the type of generator used, the output is usually 115/200 volts, 400 Hz, 3-phase. The frequency of the output of an AC generator will vary directly with the rotational speed of the generator. If an AC generator is driven directly from the engine gearbox, then its speed, and therefore the frequency of its output, will vary directly with engine speed. The output from such a generator is said to be frequency wild. In order for AC generators to be connected in parallel, their output frequencies need to be the same. So frequency wild generators cannot be connected in parallel. The output from a frequency wild AC generator may be used to power an aircraft's electrical de-icing systems, where the resistances that make up the heater mats are not affected by changing frequencies. Inverters can be used to give a constant frequency output from a frequency wild supply. A small number of aircraft types with frequency wild AC generators use a system known as the Variable Speed Constant Frequency System, or VSCF. The frequency wild AC is rectified to DC, which is used to power a static inverter, which then converts the DC to constant frequency AC. If an AC generator can be driven at a constant speed, then the output frequency will be constant. Driving the engine at a constant speed is not usually a practical proposition, so a device is required to keep the speed of the alternator constant, irrespective of the engine speed. The component used to do this is known as a constant speed drive unit, or CSDU. This is often shortened to CSD. The CSDU consists of an engine-driven hydraulic pump, the output of which drives a hydraulic motor, which in turn drives the AC generator. Hydraulic pumps and motors are fully explained in the hydraulic systems lessons. The oil, as well as being the fluid through which the mechanism operates, is also used for lubrication and cooling. It is contained within its own reservoir, entirely separate from the engine oil system. The oil circulates through an oil cooler, which uses ram air, or, on a bypass engine, fan air, as its cooling medium. The output of the hydraulic pump, and therefore the speed of the hydraulic motor, depends on the angle of a swash plate within the pump. The angle of the swash plate is controlled by a speed governor in the generator's load controller. The load controller senses the output frequency of the generator and is responsible for increasing or decreasing the output of the hydraulic pump to vary the torque output of the hydraulic motor to the generator drive in order to maintain a constant frequency output. Most CSDUs are capable of maintaining the alternator output frequency within 5% of 400 Hz. That is, between 380 and 420 Hz, throughout the engine's full RPM range. In the event of a mechanical failure in the generator, the CSDU is protected by a component known as a quill drive. This has a weak link, which will break before any major damage can be caused. Some constant frequency generators have their CSDU and generator combined in one unit, called an integrated drive unit, IDU, or integrated drive generator, IDG. There are a number of indicators on the flight deck to warn the crew of possible CSDU faults. The two main ones are low oil pressure and high oil temperature warning lights. There may also be a CSDU oil temperature indicator. The low oil pressure light will illuminate if the CSDU oil pressure drops below a predetermined minimum value. The high oil temperature light is controlled by a sensor, which is monitoring the CSDU oil outlet temperature. It will illuminate if the oil temperature becomes excessive. If either warning light illuminates, or the oil temperature on the gauge reaches the red arc, then the emergency checklist will normally call for the CSDU to be disconnected. In the event of a malfunction in the CSDU or the alternator, the engine input drive to the CSDU can be disconnected. This will allow both the drive unit and the generator to become stationary. Shown here is a simplified diagram of the drive disconnect mechanism. The disconnect unit is operated by the selection of a momentary action drive disconnect switch by a flight crew member. This operates a solenoid, which causes a mechanical separation of the input drive from the engine to the constant speed unit. The mechanism requires the unit to be rotating for it to operate, so a disconnect should only be attempted when the engine is running. Reconnection may only be done manually on the ground, following shutdown of the engine. There is a great deal of heat generated in a generator's stator windings due to the current flow through them, and some form of cooling system is required. Frequency while generators, or constant frequency generators with separate constant speed drive units, typically use ram air cooling in flight, and some means, such as a mechanical impeller, to induce airflow on the ground. Integrated drive generators use the oil from the speed control system to cool the stators. The oil is cooled in its own oil cooler. That is the end of the lesson. Here is a summary of the main points you should take from it. There are two types of rotating field AC generator in common use on aircraft. They are brushed AC generators and brushless AC generators. A brushless AC generator consists of two generators, the main generator and an exciter generator, on the same shaft. A permanent magnet generator may be used to provide the excitation current for the exciter generator. The frequency of a frequency-wild AC generator varies with engine speed. A hydromechanical CSDU keeps the generator speed constant, irrespective of engine speed. The engine input drive to the CSDU can be disconnected. This will allow both the constant speed drive unit and the generator to become stationary. If the CSDU oil pressure becomes excessively low, or the oil temperature excessively high, the CSDU should be disconnected from the engine drive. Constant frequency AC generators normally have an output of 115/200 volts, 400 Hz, 3-phase. As with DC systems, on multi-engine aircraft, constant frequency AC generators can be operated either in isolation or in parallel. On most two-engine aircraft, the generators operate in isolation, while many aircraft with more than two engines have their AC generators operating in parallel. In this lesson, we will look at parallel generator operation. You will recall that for DC generators to operate in parallel, their output voltages have to be the same. Similarly, the output voltages of all AC generators being paralleled must be the same. However, for three-phase AC machines, things are a little more complicated than that, as frequency and phase sequence also need to be taken into account. If the two generators are at different frequencies before they are connected in parallel, then damage can occur, as one generator tries to slow down and the other tries to speed up, so they must be at the same frequency before paralleling. As well as being at the same frequency, they must also be of the same phase sequence and in phase. That is to say, at any point in time, phases A, B and C on the first generator must be identical to phases A, B and C on the second generator. If two or more AC generators are connected in parallel, their frequencies will be locked together. The system frequency will be that of the generator with the highest load. You will recall the load on an AC generator, the apparent power, is made up of two components: the real or true power or load, and the reactive power or load. Each generator must take an equal share of both the real and the reactive loads. Load sharing is not required when AC generators are operating independently. Real power is the work being done by the generator in supplying the various resistive electrical services. It is the product of the in-phase current and voltage, and it is measured in watts or kilowatts. Real load is directly related to the mechanical effort or torque required to drive the generator by the engine through the CSDU. If the torque required to drive each of the generators connected in parallel is equal, then the real load on each generator, or the real power produced by each generator, will be the same. Real load sharing is achieved by controlling the CSDUs and adjusting the torque at their output shafts so that all parallel generators are experiencing the same torque. Each generator has a load controller, which controls the CSDU to maintain the basic frequency of the generator in a range of 380 to 420 Hz. When generators are connected in parallel, each load controller senses the in-phase current being supplied by its generator. The in-phase current is proportional to the real load being supplied by the generator. The load controllers are interconnected, and if there is a difference between the generator real loads, the controller of the generator taking the lower load will signal its CSDU to increase the torque input to its generator, and the load controller of the generator with the higher load will decrease the torque input to its generator, thus ensuring that each generator takes an equal share of the real load. You will recall that reactive power, or the reactive load, is a product of the vector sum of inductive and capacitive currents, which are 90 degrees out of phase with the voltage, and voltage, expressed in kilovolt amperes reactive. A generator's reactive load is therefore directly proportional to its output voltage. Reactive load sharing is achieved by controlling the voltage output of each generator that is connected in parallel, by adjusting the current flow through the voltage regulator to the exciter generator. If the parallel generator's output voltages are identical, then the reactive load on each generator will be the same. Each generator has an error detector, which is monitoring the reactive load being taken by the generator. The error detectors are interlinked. If there is a difference between the parallel generators' reactive loads, then the error detector of the generator with the higher load will signal its voltage regulator to reduce the exciter field current, and thus the generator output voltage, and the error detector of the generator with the lower load will signal its voltage regulator to increase the exciter field current, and thus its generator output voltage. That is the end of the lesson. Here are the main points that you need to remember. The output voltage of all generators being paralleled must be the same. The frequency of all generators being paralleled must be the same. The phase sequence of all generators being paralleled must be the same, and they must be in phase with each other. Real load sharing is achieved by controlling the CSDUs and adjusting the torque at their output shafts, so that all parallel generators are experiencing the same torque. Reactive load sharing is achieved by controlling the voltage output of each generator that is connected in parallel, by adjusting the current flow through the voltage regulator to the exciter generator. In this lesson, we will look at the components that are used for the control, protection and monitoring of an aircraft's AC electrical system. We will also look at the sources of backup and emergency electrical supplies. In order to see how a typical parallel generator system is controlled and monitored, we will look at the layout of a 3-generator parallel system. Notice that for each of the 3 phases of the output, there is a separate bus bar. For example, the number 1 generator bus bar, Gen Bus 1, is made up of 3 separate bus bars, A, B and C, for phases A, B and C. These bus bars are often referred to as the load bus bars, and all the electrical loads of the aircraft are shared between them. Each generator is connected to its own generator busbar through a three-phase relay, known as the generator circuit breaker or generator control breaker, GCB. The GCB can be operated automatically or be controlled from the flight deck. In the system shown here, close and trip switch lights allow the pilot to control the GCB. Visual indication of the position of the generator circuit breakers is given by indicators on the electrical control panel or the electronic display panel. A number of different annunciations are used. In the system shown, the flow bar in the close switch light is illuminated when the GCB is closed, and open is illuminated in the trip switch light when the GCB is open and the generator is disconnected from the busbar. On some aircraft types, opening of the GCB also causes the centralized warning system to operate, and there may also be an aural warning. To operate the generators in parallel, they are connected through their respective generator busbars to a synchronizing busbar by buzz tiebreakers or BTBs. A buzz tiebreaker is a three-phase relay, very similar in construction to a generator control breaker. And again, it can be controlled automatically or manually from the flight deck. Automatic control of the BTBs is provided by a synchronizing unit. The synchronizing unit monitors the phase sequence, frequency, and voltage of the synchronizing busbar and the generator to be paralleled. It will only allow the BTB to close when the correct paralleling conditions are met. The synchronizing busbar has no electrical loads connected to it. Its purpose is to allow the engine-driven generators to be operated in parallel, to allow another generator to power a failed generator's load busbars in the event of a generator or engine failure, and to allow an external power supply or power from the APU generator to be fed to the load busbars through the buzz tiebreakers when the engine generators are not operating. In a modern generator control system, the generator control unit, or GCU, is the component through which most functions of a generator's control and protection are provided. A GCU is provided for each generator. A typical GCU will monitor generator output and provide voltage regulation by controlling the exciter field current. The GCU contains protection circuitry, which will monitor for over and under voltage and frequency, and incorrect phase sequence. In the event that the generator has an under voltage fault, or an under or over frequency fault, the GCU will open the GCB, disconnecting the generator from the busbar. The GCU also contains a relay, known as the exciter control relay, generator control relay, or generator field relay. This relay controls the exciter field current supply to the generator field. If the generator develops an overvoltage or overexcitation fault, that is to say, if the output voltage or the field excitation current flow becomes excessive, the GCU will open the exciter control relay. This will cause the generator output to fall to a residual value. It will also open the generator control breaker to disconnect the generator from its load busbar. The generator control units may work together, with a component known as the Bus Power Control Unit, or BPCU, to monitor the entire system for differential current faults. Differential current faults are short circuits between bus bars, or between a bus bar and earth, causing unbalanced phase currents. The GCUs and the BPCU monitor current flow in each generator and bus bar. They will isolate a defective generator or faulty bus bar by opening the appropriate GCBs and BTBs. So a short circuit on number 1 generator bus bar would result in number 1 GCB and BTB both opening to isolate the faulty zone. And a short circuit on the synchronizing bus bar would cause all 3 BTBs to open, again isolating the faulty zone. Each generator will now be supplying its own bus bar. Load meters are used in parallel generator systems to indicate the generator real or true power and reactive power output. There is normally 1 meter for each generator. Typically, the system is configured so that the real power in kilowatts or kW is normally displayed. Pressing the button allows the reactive load in kilovolt amps reactive or kVAR to be displayed. Modern electronic display units may only show the load as a percentage of the maximum permissible load. Others don't have load indicators, with load shedding happening automatically if the load limitations are exceeded. A method of checking the voltage and frequency of each generator is usually provided. In this typical system, the voltage and frequency of any generator can be monitored on the meters by selecting the generator to be monitored on a multi-position switch. The switch can usually be positioned to show not only the supply frequency and voltage of the engine-driven generators, but also that of any other AC supply that may be available. On most modern aircraft, this information is available to the pilot on one of the electronic screens. In the event of some or all of the engine-driven generators failing, possibly because of multiple engine failures, alternative methods of supplying AC for essential services must be made available. The most commonly used methods are the ram air turbine-driven generator, the auxiliary power unit-driven generator, the hydraulic motor-driven generator, and the static inverter. The ram air turbine, or RAT, is a propeller-driven device which can be lowered into the slipstream when required. If fitted with an AC generator, it will produce an emergency source of AC power. It may be known as an LRAT. On many modern aircraft, the ram air turbine is used to drive a hydraulic pump, rather than an electrical generator. The auxiliary power unit, or APU, is usually a small gas turbine engine, normally mounted in the aircraft tail cone. This engine runs at a constant speed, and has automatic protection devices which will shut it down in the event that it develops a fault. It can be used, amongst other things, to drive 1 or 2 AC generators for ground operations prior to engine start, or, in some aircraft, for emergency electrical supplies in the air. Because the APU runs at a constant speed, its generator does not need to be driven through a constant speed drive unit. The APU generator cannot normally be paralleled with the engine-driven generators, and can be only connected to the bus bars when no other source is feeding them. Some aircraft have a hydraulic motor-driven AC generator, which can be used to supply electrical power in the event of a multiple engine-driven generator failure. As with the ram air turbine-driven generator, the hydraulic motor-driven generator is normally only used to power essential flight instruments and radios, in the event of a total generator failure. A static inverter is a solid-state device, which converts DC into AC. It is capable of supplying the aircraft with 115/200 volts, 400 Hz, three-phase AC, for the limited operation of instrument and radio services. It is powered by the aircraft batteries, or from an essential DC busbar. On the ground prior to engine start, electrical power can be supplied to an aircraft by a ground power unit. The standard modern ground power unit output is 115/200 volts, 400 Hz, three-phase AC, the same as the engine-driven generators. Ground power can be used to supply all the aircraft's electrical loads. The ground power unit circuitry must include automatic protection systems, which will ensure that ground power cannot be connected to the aircraft distribution system if the system is already being supplied by its own generators, that it cannot be connected if the phase sequence of the supply is incorrect, and that it will be rejected and switched off at source if an overvoltage fault occurs. That is the end of the lesson. The following are the main points you should take from it. Each generator is connected to its own busbar through a three-phase relay, known as the generator circuit breaker or generator control breaker. To operate the generators in parallel, they are connected through their respective generator busbars to a synchronizing busbar by bus tie breakers or BTBs. The synchronizing busbar has no electrical loads connected to it. A generator control unit, or GCU, will monitor generator output and provide voltage regulation by controlling the exciter field current. The GCU contains protection circuitry, which will monitor for over and under voltage and frequency and incorrect phase sequence. If the generator develops an overvoltage or over-excitation fault, the GCU will open the exciter control relay, causing the generator output to fall to a residual value. The GCUs, in conjunction with the bus power control unit, protect against differential current faults. Alternative methods of supplying AC power are the ram air turbine-driven generator, the auxiliary power unit-driven generator, the hydraulic motor-driven generator, the static inverter, and, on the ground, the ground power unit.
Multi-engined aircraft AC supply distribution systems will either be of the split busbar type, where each generator operates independently, or of the parallel busbar type, where each generator carries a share of all the loads. In this lesson, we will look at the split busbar type of system. In a very basic form, shown here is the general layout of an electrical distribution system for a twin-engine jet aircraft. The system will be very much the same whether the system is of the split or the parallel bus bar type. One generator is driven by and mounted on each engine, and one generator is driven by the auxiliary power unit. The feeder cables from each generator are routed through the aircraft wings and fuselage to meet at a central distribution compartment, usually beneath the flight deck or cabin floor. This distribution compartment will house many of the components we have already seen, including generator control breakers, bus tie breakers, generator control units, voltage regulators, main bus bars, the battery and the battery charger. Bus bar extensions may be found on the flight deck behind the circuit breaker panels. The split bus bar system of a two-engine aircraft uses two 115/200 volt 400 Hz three-phase AC generators driven by the engines as the primary power source. They are not designed to run in parallel and therefore do not require complex paralleling and load-sharing circuits. In particular, the phase sequence of the generators does not need to be aligned. Each generator supplies, through its generator control breaker, its own AC bus bar. And these bus bars, in turn, supply two non-essential AC bus bars. The two generator bus bars can be connected together by a normally open bus tie breaker. The essential AC bus bar is supplied from number 1 generator bus bar through a changeover relay. DC power supplies are provided by transformer rectifier units, or TRUs. The non-essential DC bus bar is supplied with 28 volts DC by a TRU connected to number 2 AC bus bar. The essential DC bus bar is supplied with 28 volts DC by a TRU connected to number 1 AC bus bar. These two bus bars are connected together through the normally closed DC isolation relay. The 24-volt aircraft battery is directly connected to the battery bus bar, which in turn is directly connected to the vital or hot DC bus bar. The battery is connected to the essential DC bus bar by the normally closed battery relay. In the event of a double generator failure, the essential AC bus bar can be supplied by a static inverter connected to the essential DC bus bar. The APU generator can supply either one or both main AC bus bars. On the ground, it can be used to power the entire aircraft. However, in flight, it may be limited to supplying only one bus bar. A suitable external AC supply can be connected to number 2 AC bus bar. From here, it can be used to power all of the aircraft's systems. This is how the system will look during normal operations, with both engine-driven generators online. The two engine-driven generators will supply their individual main and non-essential bus bars through the close contacts of their generator control breakers. The bus tie breaker will be open, keeping the generators apart. Remember, in this type of system, the generator outputs are never connected together. The essential AC bus bar will be supplied from number 1 AC bus bar. The DC essential and non-essential bus bars will be joined together by the closed contacts of the DC isolation relay. The battery relay contacts will be closed, connecting the battery to the DC essential bus bar. The battery will be supplying both the battery bus bar and the vital bus bar. If either generator should fail, its generator control breaker will open, disconnecting the generator from its bus bar. The bus tie breaker will close automatically, thereby maintaining power to all bus bars from only one generator. Loads on the non-essential bus bars can be shed if required. If necessary, the APU can be started so that its generator can be brought online to replace the failed engine-driven generator. In this case, the bus tie breaker will open once more to isolate the APU generator from the serviceable engine-driven generator. If both engine-driven generators should fail, once again their generator control breakers will open, disconnecting them from their bus bars. The main AC bus bars and their associated non-essential bus bars will no longer be powered. The battery will power the DC essential bus bar through the closed contacts of the battery relay. And the DC isolation relay will open, cutting off power to the DC non-essential bus bar. Finally, the changeover relay contacts will move over, allowing the static inverter, supplied by the battery, to power the AC essential bus bar. The only bus bars that will now be powered are the AC essential bus bar, the DC essential bus bar, the battery bus bar, and the vital bus bar. Depending on the fault, it may be possible to start the APU and use its generator to recover the lost bus bars. If the electrical system is operating on battery power alone, then the battery must be able to supply the essential services for 30 minutes on aircraft certified to EASA CS23 and for 60 minutes on aircraft certified to EASA CS25. Displayed on the screen now is the split bus bar system typically used on two-engine Airbus aircraft. The diagram is laid out in the style you can expect to find in the aircraft's aircrew manual. This system has all of the components we saw on the last system, the only major differences being that this system has two batteries and an emergency generator. You will also notice that the various electrical relays that are used to control the system are referred to by Airbus as contactors. So, for instance, the component that previously was referred to as Generator 1 control breaker is in this system known as Generator 1 contactor. Same component, different name. The engine-driven generators are connected to their individual bus bars by their generator contactors. In the event of a single generator failure, the bus tie contactors will close to supply both bus bars from one generator. On the ground, external power or the APU generator can supply all services. In flight, the APU generator can be used to replace a failed generator. The AC essential bus bar can be supplied from a number of sources. It is normally supplied from AC bus bar 1. But it can be supplied from AC bus bar 2. If neither of these bus bars is available, then the emergency generator, driven by a hydraulic motor, supplied from the aircraft's hydraulic system, can be used. Finally, if hydraulic power is not available, the static inverter supplied by the batteries through the DC essential bus bar can be used to power the essential AC bus bar. DC bus bars 1 and 2 and the essential DC bus bar are normally supplied by transformer rectifier units connected to their respective AC bus bars. The DC battery bus bar connects numbers 1 and 2 DC bus bars together. It also allows power from these bus bars to charge the batteries. If the essential DC bus bar loses its normal power supply, it can be supplied from either one or both of the batteries. This system is almost completely automatic in its operation. In the event of a failure or failures, all configuration changes are carried out automatically. The pilot, however, does have a control panel with a limited number of switch lights on it. When the system is operating normally, all lights on the panel are out. The generator 1 and 2 switch lights allow the pilot to switch off the engine-driven generators by opening their respective generator contactors. The fault light in the switch will illuminate if the generator contactor has been opened by the automatic control system because of a generator fault. The APU and external power available lights illuminate green when the associated power supply is available with its voltage and frequency within limits. The APU generator will come on as required unless the pilot pushes the switch light to lock it off. Pushing the external power switch light will bring the external supply online. The integrated drive generator or IDG disconnect switch lights each have a fault light which will illuminate if the associated IDG oil pressure is low or oil temperature is high. Pushing the guarded switch light will disconnect the associated IDG from its engine. The bus tie switch allows the pilot to lock the two bus tie contactors open. As we have said, the essential AC bus bar is normally supplied from AC bus bar 1. The AC essential feed switch allows the pilot to select AC bus bar 2 as the source of supply for the essential AC bus bar. The two battery switches allow the pilot to disconnect the battery charging circuits by locking open the battery charge contactors. The fault lights in the battery switch lights illuminate if the battery charging current is excessive. The galley switch light allows the pilot to cut off the power supplies to the galleys or shed the galley loads. This may be required when operating with only one generator online. Finally, the voltages of the two batteries are continuously displayed on the panel. Operation of the system can be monitored on the aircraft's electronic display screens. The oil temperatures of the engine-driven IDGs are displayed here. The output voltages and frequencies of all operating generators is displayed, along with the load being taken by the generator as a percentage of the generator's capacity. The output voltages and current being supplied by numbers 1 and 2 transformer rectifier units are displayed here. The battery voltages are also displayed along with any charge or discharge current. In the event of a malfunction, the display will change to show the new configuration. Here, for instance, generator 1 has failed and it has been replaced by the APU generator. That is the end of the lesson. The most important point to remember from this lesson is that in split busbar type systems, the various sources of AC power are never connected to the same busbar. Here are the other points you should take from the lesson. Because the generators are never operated in parallel, phase sequence does not need to be aligned between the generators. In most systems, the essential AC busbar is normally supplied from number 1 AC busbar. In the event of the loss of all generators, a static inverter, powered from the battery, will supply the essential AC loads. In the event of a single generator failure, busbars 1 and 2 are connected together by the bus tie breaker. On the ground, an external power supply can be used to power all of the busbars. When you are happy with these points, continue to review the Airbus system circuit diagram. Here is the Airbus system in its normal in-flight configuration. Spend a few moments making sure you are familiar with it before you finish the lesson. Multi-engine aircraft AC supply distribution systems will either be of the split busbar type, where each generator operates independently, or of the parallel busbar type, where each generator carries a share of all the loads. In this lesson, we will look at a parallel busbar type of system, as fitted to a 4-engine Boeing aircraft. Each of the four 115/200 volt, 400 Hz, 3-phase engine-driven integrated drive AC generators, or IDGs, is connected to its respective load busbar by a generator control breaker, or GCB. Busbars 1 and 2 can be connected to the left synchronizing busbar through bus tie breakers. Busbars 3 and 4 can be connected to the right synchronizing busbar in the same way. All loads are connected to the load busbars. The synchronizing busbars have no loads attached to them. The left and right synchronizing busbars can be connected together by the split system breaker. The auxiliary power unit, or APU, drives two generators. APU generator 1 connects to the left synchronizing busbar and APU generator 2 to the right. The APU generators do not have constant speed drive units, so they cannot be operated in parallel with any other generators. Two AC external power cards can be connected into the electrical system. One connects to the left synchronizing busbar and the other to the right. As with the APU generators, external power cards cannot be operated in parallel with any other power source. Operation of the system is almost fully automatic. However, there is a control panel which firstly keeps the pilot informed of the current configuration, and secondly allows him to override certain functions if required. We will have a look at the operation of the system and the indications the pilot can expect to see, starting with the aircraft stationary on the ground with no engines running. If the APU is running and the outputs from its generators are satisfactory, available lights will be illuminated in their switch lights. Similarly, if external power cards are connected to the aeroplane and their output voltages and frequencies are satisfactory, available lights will be illuminated in their switch lights. The pilot can connect one of these power supplies to the busbars by pressing its switch light. This will connect the selected source to the left or right synchronizing busbar. The split system breaker is normally closed, unless there is a fault, so the supply will also be fed to the other synchronizing busbar. The bus tie breaker, or BTB switch lights, are normally latched in with auto-illuminated. In this position, the BTBs will remain closed unless there is a fault. Therefore, the selected source will power all four load busbars through their BTBs. If an APU generator or external power supply is connected to the other synchronizing busbar, then the split system breaker, or SSB, will automatically open to separate the two sources of supply. Each of the four engine-driven generators has a generator control switch light and a guarded drive disconnect switch light. Each drive disconnect switch light has an amber drive light which will illuminate if its associated IDG oil pressure is low or oil temperature is high. The guard can then be raised and the switch operated to disconnect the IDG from the engine. Remember that the engine must be running at a minimum of idle RPM before this action is taken. At the moment, the drive lights are all illuminated because the engines aren't turning. Each generator control switch light has a white on light and an amber off light in it. With the switch light latched in its normal position, the on light will be illuminated. In this switch position, the generator control breaker is armed to close when the generator output is within limits and to open when it is not. The amber off light monitors the position of the GCB. It is illuminated when the GCB is open. The pilot will first start number 4 engine. As the engine accelerates and the IDG begins to rotate, the IDG oil pressure will rise and the drive light in the disconnect switch will go out. When the generator output voltage and frequency are within limits, because the APU generators or external power cannot be operated in parallel with the engine-driven generators, the automatic control system will first disconnect the APU generator or external power from the synchronizing bus bar, and then close the number 4 GCB. Number 4 generator will now supply its load bus bar, and through its BTB the right synchronizing bus bar. From here, bus bar 3 will be supplied through its BTB, and the left synchronizing bus bar through the split system breaker. Bus bars 1 and 2 will be powered from the left synchronizing bus bar through their BTBs. Thus, generator 4 will be supplying all of the loads. As each subsequent engine is started, the output voltage, frequency and phase rotation of its generator are adjusted to align with the voltage, frequency and phase rotation of the generator or generators already supplying the bus bars. And when all are aligned, the associated GCB will close, allowing the generators to operate in parallel. The APU will be stopped and external power will be disconnected prior to taxi. So with all generators operating normally, the control panel will look like this. In the event of a fault on an individual generator or an engine failure, the associated GCB will automatically open and the other in-parallel generators will carry the load with no loss of supply. If there is a short circuit fault on a bus bar, the breakers surrounding the faulty bus bar will automatically open to isolate the area with the short circuit. A short circuit on the left synchronizing bus bar, for instance, will cause the split system breaker and bus tie breakers 1 and 2 to open, isolating the affected bus bar. The system is almost completely automatic. The pilot does not normally make any selections apart from selecting the APU generators or external power on. If it is required, he can latch out any of the GCB or BTB switch lights, locking the associated breaker open. You will notice that there is no indication on the control panel of the status of the split system breaker. It is, however, possible to view a synoptic of the system on one of the aircraft's electronic screens, and this includes the SSB. This picture shows the system operating normally with the SSB closed. The synoptic display also reflects any abnormal system configurations or faults. In this example, number 3 bus tie breaker is open, and number 2 IDG has either a high oil temperature or low oil pressure fault. DC loads are supplied from transformer rectifier units connected to the load bus bars. Emergency AC power is provided by a static inverter supplied by the aircraft battery and emergency DC power directly by the battery. These systems are connected in much the same way as in a split bus bar system and are fully explained in the split bus bar systems lesson. That is the end of the lesson. Here is a summary of the main points. The generators are connected to their load bus bars by generator control breakers. The load bus bars carry all of the loads. Bus tie breakers connect the load bus bars to the synchronizing bus bars. The synchronizing bus bars are connected together by the split system breaker. APU generators or external power supplies cannot be operated in parallel with any other power source. The output voltage, frequency and phase rotation of each generator is adjusted to align with the voltage, frequency and phase rotation of any generator or generators already supplying the bus bars before it is allowed to connect to the bus bars.
One of the biggest advantages that an AC supply has over a DC supply is the ease with which the value of alternating voltage can be raised or lowered with great efficiency by the use of transformers. It can also easily be converted into DC by the use of diode rectifiers. Transformers and diode rectifiers are often used together in transformer rectifier units. In this lesson, we will look at the operation of both transformers and diodes. We know from previous lessons that when a current passes through a conductor, a magnetic field is produced, and that the strength of the magnetic field can be enhanced by wrapping the wire in a coil and giving it a soft iron core. We also know that when a conductor is moved through a magnetic field, cutting the lines of flux, an electromotive force is induced in the conductor. It is these principles that are used in transformers. A simple transformer consists of two electrically separate coils of wire wound around two opposite sides of a laminated soft iron core. The coils are known as the primary and the secondary windings. The primary winding is connected to an AC supply, and the output is taken from the secondary winding. The alternating voltage and current in the primary winding creates an alternating flux, which flows through the core and cuts through the coils of the secondary winding. This induces an EMF in the secondary winding, which is available as the output AC voltage. If a load is placed across the terminals of the secondary winding, then an alternating current will flow in the circuit. In electrical diagrams, a transformer is usually indicated by the symbol shown here. The transformation ratio of a transformer is the ratio of the number of turns or coils of wire on the secondary winding, N2, to the number of turns of wire on the primary winding, N1. The transformation ratio is also the ratio of the output voltage to the input voltage. A coil with 100 turns of wire on the secondary winding and 400 on the primary will have a transformation ratio of 100 divided by 400, or 0.25. We can now use this ratio to calculate the output voltage of the transformer. If, in this example, the input AC voltage was 115 volts, the output voltage would be 115 multiplied by 0.25. or approximately 29 volts AC. A transformer with a transformation ratio greater than 1 is known as a step-up transformer, whilst a transformer with a ratio less than 1 is known as a step-down transformer. Transformers are almost 100% efficient in their transfer of power from the primary to the secondary windings. So for all practical purposes, we can say that the power that goes into a transformer equals the power that comes out of it. From this, we can say that the product of the voltage and the current in the primary winding will be equal to the product of the voltage and current in the secondary winding. It is important that the input supply to the primary coil of a transformer is of the correct frequency. Transformers are inductive devices, and if the input frequency is low, it is possible that the transformer will overheat due to excessive current flow. The output of a three-phase AC generator can be transformed by using either 3 single-phase transformers or a 3-phase transformer, which consists of a laminated core with 3 limbs on which are wound the 3 sets of primary and secondary windings. An auto transformer uses a single winding on a laminated core with a pick-off at a predetermined point along the coil. As you can see, part of the coil carries both the primary and secondary current because it is common to both windings. Auto transformers are less expensive than 2-coil transformers because they use less materials. However, one of the major advantages of 2-coil transformers is that the primary and secondary circuits are electrically isolated from each other, and this is not so in auto transformers, so their use is limited to situations where this is not important. Where AC is required for the operation of instruments on the aircraft, auto transformers can be used to either step down or step up the source supply to the required voltage. The supply usually required for instruments is 26 volts AC. A rectifier is a device which will convert alternating current into direct current. The most common rectifier in use in aircraft systems is the solid-state diode rectifier. The electrical symbol for a diode rectifier is shown here. The diode is a semiconductor device, and its operation is fully explained in the lesson on semiconductors. It has a very low resistance to current flow in the direction of the arrowhead, and a very high resistance in the other. If a diode rectifier is placed in an AC circuit, it will allow current to flow through the load in one direction only. This is termed half-wave rectification. Current will flow through the load in one half cycle, but in the other half cycle, when the polarity of the voltage is reversed, the flow of current will be blocked. This method of rectification will therefore produce pulses of DC in the secondary circuit, with gaps between the pulses. To produce DC without gaps in the pulses, a full-wave bridge rectifier, as seen on the screen, can be used. The bridge has a diode rectifier on each leg. The AC supply is connected across the bridge at points A and B, and the output is taken from points C and D. In one half of the cycle of the AC input, point A will be positive and point B negative, so current will flow through the bridge and the load in the direction shown. In the next half cycle, the polarity will be reversed, making point A negative and B positive. However, because of the arrangement of the diodes, the current flows through the load in the same direction as before. The output of a bridge rectifier consists of pulses or ripples of DC. These usually need to be smoothed electronically before being used. A much smoother supply, without large peaks and troughs, can be produced from a three-phase supply by using a three-phase bridge rectifier. A three-phase rectifier superimposes the full-wave rectified output from all three phases on top of each other. Thus it produces a much smoother output than a single-phase rectifier. The output of a three-phase rectifier can therefore be considered to be of a steady DC voltage. There is another type of diode rectifier you may come across, known as the Zener diode rectifier. The symbol for a Zener diode is shown here. This type of diode, again, allows unrestricted current flow in one direction, but if the polarity of the voltage is reversed, it will block current flow, until at a predetermined voltage drop across the diode, it will allow reverse current to flow without restriction. Zener diodes are often used in voltage regulator circuits. Transformer rectifier units, or TRUs, convert AC at one voltage to DC at another voltage, in order to supply the DC needs of an aircraft with an AC distribution system. The TRU combines the transformer and rectifier in one unit. The input supply is usually 115/200 volts, 400 Hz, three-phase AC, and the output 28 volts DC. The TRU current output can normally be monitored by the pilot, either on a gauge or an electronic screen. Some aircraft types, which have a frequency-wild AC distribution system, use transformer rectifier units to feed static inverters to supply the aircraft's normal constant frequency requirements. This is done by using the TRU to change the frequency-wild AC into DC, and then using the DC to power the inverter, which will produce a constant frequency AC output. That is the end of the lesson. Here are the main points that you need to take from it. Transformers are used to raise or lower the voltage in an AC electrical system. An autotransformer has only one coil. Autotransformers with an output voltage of 26 volts are often used to power instruments. In a step-up transformer, the output voltage is greater than the input, but in a step-down transformer, it is lower. The power in the primary winding of a transformer is equal to the power in the secondary winding. The input supply to the primary coil of a transformer must be of the correct frequency. If the input frequency is low, it is possible that the transformer will overheat due to excessive current flow. A diode rectifier has a very high resistance to current flow in one direction and a very low resistance in the other. A bridge rectifier produces an output of full-wave rectified DC. A three-phase bridge rectifier produces a steady DC output voltage. A Zener diode acts in the same manner as a normal diode until a predetermined reverse voltage is reached, at which point it allows unrestricted current flow in the reverse direction. Transformer rectifier units, or TRUs, convert AC at one voltage to DC at another voltage, in order to supply the DC needs of an aircraft with an AC distribution system.
In this lesson, we will look at the construction and operation of electric motors using AC as their power supply. The great advantage that an AC motor has over its DC counterpart is that it doesn't require the use of a commutator, so the problems of arcing at the brushes is greatly reduced or even eliminated. Whether the AC motor is single or multi-phase, the principle of operation is the same. The motor is made up of a stationary part known as the stator and a rotating assembly known as the rotor. The stator is most commonly fed from a three-phase AC supply. The stator windings are set 120 degrees apart, with the pair of poles for each winding being supplied from one of the three phases. This arrangement produces a rotating magnetic field around the stator. To see how the rotating magnetic field is produced, we will look at one half cycle of the AC supply. When the current flow in their phases is positive, the poles marked A, B and C are magnetic north poles, and those marked A1, B1 and C1 are south poles. When a phase's current flow is negative, its magnetic poles are reversed, with A1, B1 and C1 becoming magnetic north poles and A, B and C becoming souths. If we start at point 1 on the graph, you can see that phase A is at its positive peak. So, pole A has a strong north magnetic pole, and A1 a strong south pole. Phases B and C are both negative, so poles B1 and C1 have weaker north poles. The magnetic fields will look like this. If we move the sequence onto part 2, we can see that the C phase current is now at its negative peak, so the C1 to C magnetic field is at its strongest. A phase has moved away from its peak, so the strength of the A and A1 magnetic poles is reducing, and B phase has moved from negative to positive. So now pole B is now a north, and pole B1 a south. Moving on to position 3, B phase is now at its positive peak, so there is a strong magnetic field from pole B to B1. Both A and C phases are negative, so poles A1 and C1 are weak norths. At position 4, A phase is now at its negative peak, so there is a strong magnetic field from pole A1 to A. B and C phases are both positive, so poles B and C are weak norths. This process continues as each phase moves through its cycle, causing the total magnetic field to rotate at a speed equal to the frequency of the supply. If two phases of the supply to a three-phase rotating field are reversed, the direction of rotation of the field, and thus that of the rotor being driven by it, will be reversed. There are two types of rotating field AC motors in common use in aircraft installations. They are known as synchronous motors and induction motors. We will look at them both, beginning with induction motors. The induction motor gets its name from the fact that an alternating current is induced in the rotor by the rotating magnetic field in the stator. It is the most commonly used AC motor because of its simplicity, its robustness, and because it is relatively cheap to produce. The rotor usually consists of a cylindrical laminated iron core which has a number of longitudinal bars of copper evenly spaced around the circumference. These bars are joined at either end by rings of the same material to form a composite structure called, because of its shape, a squirrel cage. The rotor bars are made of very low resistance material so that a large current can flow through them. The rotating magnetic field produced in the stator cuts through the bars of the rotor, which along with the end rings form a closed circuit of low resistance. The resultant induced voltage creates a relatively large current flow in the squirrel cage assembly, as shown in this simplified diagram. This current flow sets up its own magnetic field, which interacts with the rotating field of the stator to produce a torque, causing the rotor to turn in the same direction as the rotating field of the stator. The speed of an induction motor is determined by the frequency of the supply and the load on the motor. The rotor never quite reaches the speed of the rotating field. The reason for this is because if it did, then the squirrel cage bars would not be cut by any lines of flux from the rotating field, and no voltage would be induced in them. The difference between the speed of the rotating field, or the synchronous speed, as it is known, and rotor speed is called the slip speed, or rotor slip. Because of the difference in speed between the stator field and rotor, the induction motor is sometimes referred to as being asynchronous. If the load on the motor is increased, the rotor will tend to slow down. This will increase the amount of cutting of lines of flux and increase the current flowing in the squirrel cage, which in turn increases the strength of the induced magnetic field, which increases the motor torque to compensate for the increased load, maintaining the motor speed virtually constant. Most induction motors fitted on aircraft are of the three-phase type. However, single-phase induction motors can also be used. Single-phase induction motors are not self-starting. That is to say, when power is applied, they will not rotate. The most common method of starting a single-phase induction motor is by use of a split-phase winding at 90 degrees to the main winding. The current in the split-phase winding is made to lead or lag the current in the main winding by 90 degrees in order to change the pulsating field into a rotating one. This can be done by the use of capacitors, inductors, or resistors. Occasionally, the failure of one phase of the supply to a three-phase induction motor does happen. If the motor is lightly loaded, then it will probably continue to run at about half its normal speed. The fault usually becomes apparent the next time an attempt is made to run the motor, when it will not start to rotate. If a bar magnet is suspended in a rotating magnetic field, it will lock into the field with its south pole staying with the rotating north pole and its north pole staying with the rotating south. The magnet will therefore rotate synchronously with the field, at the same speed as it. This is the principle of operation of the synchronous motor. A practical synchronous motor, rather than using a bar magnet, has a rotating coil on a soft iron core, energized with DC through slip rings, causing it to act as an electromagnet. In the same way as the bar magnet did, it lines up with the field created by the stator, and if the field turns, the rotor turns with it. The speed of rotation of a synchronous motor depends upon the frequency of the supply and the number of poles. Since in most cases the supply frequency is constant, then so is the motor speed. We can transpose the formula we use to calculate a generator's frequency to work out the speed of the motor in revolutions per minute, or RPM. If a synchronous motor with 4 poles is supplied with a constant frequency 400 Hz supply, it will rotate at a constant 12,000 RPM. One disadvantage of the synchronous motor is that it is not self-starting. To obtain the initial rotation, some induction windings have to be added to the rotor to assist in bringing it up to synchronous speed. This is often achieved by fitting a squirrel cage type assembly to the rotor. Synchronous motors are often used on aircraft to indicate engine RPM. A small 3-phase AC generator, known as a tacho generator, is driven by the engine, so that the frequency of its output will be directly proportional to engine speed. The electrical output is used to drive a synchronous motor in the RPM indicator. The operation of this instrument is fully explained in the instrument's lessons. That is the end of the lesson. Here is a summary of the main points. An AC motor is made up of 2 parts, a stationary stator and a rotating rotor. AC motors use a rotating magnetic field in the stator to drive the rotor. If 2 phases of the supply to a 3-phase rotating field are reversed, the direction of rotation of the field, and thus that of the rotor being driven by it, will be reversed. An alternating current is induced in the rotor of an induction motor by the rotating magnetic field in the stator. The difference between the speed of the rotating field of an induction motor and the speed of the rotor is known as the slip speed, or rotor slip. In a synchronous motor, the rotor rotates at the same speed as the rotating field. Here is the formula for calculating the speed of rotation of a synchronous motor.
Semiconductors have had a monumental impact on our society. Semiconductors are used to make microprocessor chips, as well as being used in the production of diodes and transistors. Semiconductors are at the heart of all electronic devices. Modern aircraft use electronic components in many of their systems, including automatic flight controls, navigation and engine control systems. In this lesson, we will look at what a semiconductor is, and at the makeup and operation of diodes and transistors. We will begin the lesson by reviewing the atomic construction of conductors and insulators. The simplest atom is the hydrogen atom. It consists of a nucleus containing 1 proton, positively charged, with 1 electron, negatively charged, orbiting about the nucleus. Conductors and insulators have more complex atoms, with greater but equal numbers of protons and electrons, with the latter orbiting the nucleus in multiple orbits or shells. The nuclei of all atoms, except hydrogen, also contain neutrons. They play no part in the electronic process, so we can ignore them. The electrons in the outer shell of an atom are known as the valence electrons. Electrons in the outer shells may be less tightly bonded to their parent atom than those on the inner shells. and are free to move from one atom to the next. These valence electrons, known as free electrons, form the basis for electrical current flow within the material. Conductors possess large numbers of free electrons. This allows current to flow easily through the material. Gold, silver and copper are all examples of good conductors. Insulators possess few free electrons. This means that it is difficult to get current to flow through them. Mica and glass are examples of good insulators. Semiconductors, as their name would imply, fall somewhere between conductors and insulators. Silicon and germanium are the two semiconductor elements that are used in the production of electronic components. By far the most commonly used is silicon, which is a very common naturally occurring element. It is, for instance, the main element in sand. Silicon and germanium, along with carbon, have a unique property in their electron structure. Each has 4 valence electrons in its outer orbit. As shown in this simplified diagram, the 4 electrons form perfect bonds, known as covalent bonds, with 4 neighbouring atoms creating a lattice. All of the outer electrons in a pure silicon or germanium crystal are involved in perfect covalent bonds, so they can't move around. A pure silicon or germanium crystal is somewhere between a conductor and an insulator. Very little electricity will flow through it. You can change the behavior of silicon or germanium and make it into a conductor by a process known as doping. In doping, a very small amount of an impurity is mixed into the silicon or germanium crystal. Doping produces 2 new materials, known as N-type and P-type material. In N-type doping, antimony or arsenic is added to the semiconductor material in small quantities. Antimony and arsenic each have 5 outer electrons. So when they get into the silicon or germanium lattice, the 5th electron has nothing to bond to, so it's free to move around. As you can see in this simplified diagram, when an EMF is applied, the free electrons move through the material from atom to atom, creating a current flow. N-type material is a good conductor. Electrons have a negative charge, hence the name N-type. However, it should be noted that the material itself remains electrically neutral. There are always an equal number of protons and electrons within the material. In P-type doping, aluminium or indium, each of which has only 3 outer electrons, is the dopant. When mixed into the semiconductor material lattice, they form holes in the lattice where an electron has nothing to bond to. Holes can appear to conduct current. A hole happily accepts an electron from a neighbour, moving the hole to the neighbouring electron. As you can see in this simple animation, when an EMF is applied, the hole appears to move through the material from right to left, causing an electron flow in the opposite direction. The absence of an electron creates the illusion of a positive charge, hence the name P-type. P-type semiconductor material is a good conductor. Again, it should be noted that it possesses no electrical charge, there being an equal number of electrons and protons in the material at all times. A junction diode, which consists of a piece of N-type material fused to a piece of P-type material, is the simplest possible semiconductor device. In this diagram, we're using white circles to indicate holes, and green dashes the free electrons in the two materials. At the junction of the two materials, some free electrons from the N-type material migrate across the boundary to fill holes in the P-type, and similarly, holes migrate the other way. This migration produces positive ions in the N material and negative ions in the P material. This in turn produces a charged region at the junction, known as the depletion layer, and creates an electrical potential, known as the barrier potential, across the junction. The positive and negative ions in the depletion layer repel holes and electrons, preventing further electron or hole movement between the materials. The barrier potential may be represented as an imaginary battery, although it should be remembered that the regions of increased positive and negative charge exist only across the junction. The material as a whole possesses no electrical charge. If we now connect an external EMF across the material, with the positive terminal connected to the N-type material and the negative terminal to the P, electrons will be attracted to the positive terminal and will be pulled from the N side of the junction. Similarly, holes will be attracted away from the P side of the junction towards the negative terminal. This increases the number of positive and negative ions, deepening the depletion layer. Apart from a very small leakage current, this deepening of the depletion layer prevents current flow across the junction. The junction is said to be reversed biased. If the polarity of the external EMF is reversed, so that the positive terminal is connected to the P-type material and the negative terminal to the N, the holes in the P-type material will now be pushed to the right, towards the junction, and the free electrons in the N-type to the left, again towards the junction. In the junction region, the free electrons and holes combine. Thus the barrier potential is overcome, and current will flow freely through the junction. In this configuration, the junction is said to be forward biased. The junction diode then acts as a rectifier, allowing current to flow through it in one direction only. As a reminder, here is the electrical symbol for a diode rectifier. We will now look at the bipolar or junction transistor. There are two types of junction transistor. They are known as the NPN transistor and the PNP transistor. The NPN transistor consists of a thin layer of P-type material sandwiched between two pieces of N-type material, whilst the PNP transistor has a thin layer of N-type material sandwiched between two pieces of P-type material. The three regions of either type of transistor are known as the collector, the base, and the emitter. The circuit symbol for each transistor is shown here. As you can see, the symbols differ only in regard to the direction of the arrow between the base and the emitter. The arrow always points in the direction of conventional current flow. For an NPN transistor, it points from base to emitter, and for a PNP, from emitter to base. The theory governing the flow of current in a transistor is complex and beyond the scope of this course, so we will limit ourselves to a very basic explanation of the operation. We will have a look at the operation of the two types of transistor, beginning with the NPN type. If we apply an EMF across the collector-emitter region of an NPN transistor, as shown here, remembering back to the junction diode, one of the junctions will be forward biased, but the other will be reverse biased, so no current will flow in the circuit. However, if we apply a small EMF, known as a bias voltage, across the base emitter region, changes take place in the material which will allow current to flow freely from the collector to the emitter. The ability of a transistor to control a large collector-emitter current by means of a small base emitter current means it can act as a switch or electrical relay by turning the small base emitter EMF on and off, thus controlling the current flow in the collector-emitter circuit. The transistor can also act as an amplifier. If a small AC voltage signal is superimposed on the bias voltage, it will produce directly proportional variations in the collector-emitter current. A PNP transistor's operation and function is similar in all respects to that of an NPN transistor, except that the polarities of the applied EMFs are reversed. So now the conventional current flows from the emitter to the base, and from the emitter to the collector. In conjunction with the junction diode and other electronic components, such as resistors, capacitors, and inductors, the applications for the transistor are almost limitless. Furthermore, the ability to control precisely those areas to which doping is applied means that all of these components can be incorporated into a highly sophisticated and complex circuit within a single small piece of silicon or silicon chip. That is the end of the lesson. Here are the main points. Semiconductors, as their name would imply, fall somewhere between conductors and insulators. Germanium and silicon are the two semiconductor elements that are used in the production of electronic components. You can change the behavior of silicon or germanium and turn it into a conductor by a process known as doping. In N-type doping, antimony or arsenic is added to the semiconductor material in small quantities, producing free electrons. In P-type doping, aluminium or indium is the dopant. This produces holes in the lattice structure. A junction diode consists of a piece of N-type material fused to a piece of P-type material. A junction diode allows current to flow freely through it in one direction, but resists current flow in the opposite direction. A transistor can act as either an electrical switch or as an amplifier.
In this lesson, we will look at logic gates. Logic gates perform basic logical functions and are the fundamental building blocks of digital integrated circuits. Digital computers use digital data in their operations. This form of data has only two levels of voltage. Digital circuits are two-state circuits. They are either on or off. The term logic gate refers to a switching action or actions. Simple mechanical switches can be used to produce logic functions, but in modern circuits the switching is done by solid-state electronic devices. Some circuits may have only a few logic gates, while others, such as microprocessors, may have millions of them. By combining thousands or millions of logic gates, it is possible to perform highly complex operations. Normally, when working on paper, we count from 0 to 9. This is the decimal number system. Digital computers use the on-off, two-state or binary number system. A full explanation of the binary number system is beyond the scope of this lesson. But quite simply, the only digits used are 0 and 1. Decimal 0 is equal to binary 0. And decimal 1 equals binary 1. But after that, the two systems change. Decimal 2 is represented in the binary system by 1, 0. Decimal 3 by 1, 1. And so on, as shown on the screen. Logic gates take an input of one or more binary values of either 0 or 1 and output a single value of 0 or 1. You may find binary 1 also expressed as on, true, high, closed, or engaged, and binary 0 as off, false, low, open, or disengaged. In electrical circuits, the actual voltage levels required to achieve a binary 1 or binary 0 may vary, depending whether positive or negative logic is being used. If positive logic is used, a binary 1 equals a high voltage level, and a binary 0 equals a low voltage level. The actual voltage values may be either both positive or both negative, or one positive and one negative. The only stipulation for positive logic is that a binary 1 is created by a more positive voltage than a binary 0. Most digital computer systems employ positive logic. The negative logic concept defines binary 1 as the lower voltage value and binary 0 as the higher or more positive voltage value. Although less popular, negative logic is used in some systems in order to meet certain design parameters. Truth tables are a systematic means of displaying binary data. They illustrate the relationship between a logic gate's inputs and outputs. This type of data display can be used to describe the operation of a gate. There are 6 commonly used logic gates. They are the AND, the OR, the invert or not, the NOR, the NAND, and the exclusive OR gate. The name of each gate represents the function it performs. Each logic gate has a symbol of a specific shape. The purpose of the symbol is to specify the relationship between the inputs and outputs of the circuit, without the necessity to show the entire electrical workings of it. The inputs are always listed on the left of the symbol and the outputs on the right. We will look at each type of gate, beginning with the AND gate. Shown on the screen is the symbol for an AND gate. The AND gate is used to represent a situation where all inputs to the gate must be 1 to produce a 1 output. If any input is a 0, the output will be 0. The AND gate can have 2 or more inputs. We can build up the truth table for this 2-input AND gate by looking at all of the possible combinations of inputs and outputs. To help us with this, we can represent the AND gate by the electrical circuit shown here. The two switches in series represent the inputs, and the light bulb the output. With the switch open, it represents binary 0, and when it is closed, binary 1. If both switches open, the light will be out, indicating an output of 0. If switch B is closed with switch A open, the output will still be 0. Similarly, if switch A is closed with switch B open, the output will be 0. Only when both switches are closed will the bulb illuminate, indicating an output in binary terms of 1. Because all inputs to this gate need to be binary 1 to produce an output of binary 1, this gate is sometimes referred to as the all or nothing gate. The next gate we are going to look at is the OR gate. The symbol for this gate is being displayed on the screen. The OR gate may have any number of inputs. If one or more of these inputs is 1, then the output will be 1. The OR gate will only give a 0 output if all of its inputs are 0. A 2-input OR gate can be represented electrically by this circuit with the switches in parallel. If switch B is closed, or switch A is closed, or both switches are closed, the light will illuminate. Only if both switches are open will the light go out. This gate is sometimes referred to as the any or all gate. Spend a moment studying the truth table before moving on. The invert gate, sometimes known as the NOT gate, is represented by this symbol. This gate contains only one input and one output, and is used to reverse the condition of the input signal. It is most often used in conjunction with other gates. Electrically, an invert circuit can be represented by a switch controlling a relay, the contact of which is made when the relay is de-energized. With the switch open, position 0, the light is on, representing an output of 1. But with the switch closed, position 1, the light is out, representing an output of 0. As you can see, there is a very simple truth table for an invert or NOT gate. This symbol represents the NOT AND or NAND gate. Notice that it is the same as an AND gate apart from the small circle at the output. The NAND gate is an AND gate with an inverted output. The output of this gate will be 1 if any input is 0. This is the exact opposite of an AND gate. Here is an electrical circuit which will function as a 2-input NAND gate. As you can see, with the relay de-energized, the light will be illuminated, indicating an output of 1. The two switches A and B are in series and are controlling the electrical supply to the coil of the relay. Only if both switches are placed closed will the relay be energized, causing the light to go out and indicating an output of 0. Here is the truth table for the NAND gate. Spend a moment studying it before moving on. Here is the symbol for a NOT OR or NOR gate. Like the NAND gate, this is the same as an OR gate, but with a circle added on the output. The NOR gate is an OR gate with an inverted output. This results in a gate where if one or more input is 1, the output will be 0. As with the NAND gate, the NOR gate can be represented by an electrical circuit containing a relay which is controlled by a number of switches. Only this time, the switches controlling the electrical supply to the coil of the relay are in parallel. With both switches open, the relay is de-energized and the light is illuminated, indicating an output of 1. If either switch or both switches is closed, the relay will be energized and the light will go out, representing an output of 0. Here is the truth table for the NOR gate. Again, spend a moment studying it before moving on to see the final gate. The final gate we want to examine is the exclusive OR gate. Here is the symbol for this gate. This gate always has two inputs and it produces an output of 1 when the two inputs are not the same. That is to say, for an output of 1, one input must be 1 and the other 0. The electrical representation of the exclusive OR gate is quite complicated, as you can see. You may, if you wish, spend a moment studying the diagram to see how it works. However, it is of little importance. The important thing with this, and indeed all of the gates, is to remember what the output will be with the various inputs. Here is the truth table for the exclusive OR gate. Spend a moment studying this before moving on to the lesson summary. Here is a summary of the main points from the lesson. The AND gate is used to represent a situation where all inputs to the gate must be 1 to produce a 1 output. If any input is a 0, the output will be 0. If one or more of the inputs to an OR gate is 1, then the output will be 1. The OR gate will only give a 0 output if all of its inputs are 0. The invert or NOT gate contains only one input and one output, and is used to reverse the condition of the input signal. The NOT AND or NAND gate is an AND gate with an inverted output. The output of this gate will be 1 if any input is 0. The NOT OR or NOR gate is an OR gate with an inverted output. This results in a gate where if one or more inputs are 1, the output will be 0. The exclusive OR gate always has two inputs, and it produces an output of 1 when the two inputs are not the same. That is to say, for an output of 1, one input must be 1 and the other 0. When you are ready, continue to see a review of the truth tables for the 6 logic gates. The truth tables for the 6 logic gates are now being displayed on the screen. A computer may be defined as a device or set of devices that can store data, and a program that operates on the data. A general-purpose computer can be programmed to solve any reasonable problem expressed in logical and arithmetical terms. The first fully operational general-purpose computer, electromechanical and using binary digits, was the Z3, built in Germany in 1941 by Konrad Zuse. Basically, there are two types of computer, analog and digital. By far the most common is the digital computer or microprocessor, which now plays a part in most aspects of everyday life. In this lesson, we will have a quick look at the analog computer, and then examine the numbering systems used to manipulate data in digital computers. An analog computer uses continuous physical variables such as voltage, pressure, or mechanical movement to represent and manipulate the measurements it handles. Analog computers can have a very wide range of complexity. The manually operated navigation computer, with which you will become familiar, is a simple example of a mechanical analog computer. Analog computers are used as electronic models or analogues of mechanical or other systems in cases where conducting experiments on the system itself would be costly, time-consuming, or dangerous. For example, when designing an aircraft wing or any structure where motion can occur, the engineer must know beforehand how it will react to various physical variables, such as wind speed, turbulence, applied load, and temperature. In recent years, analog computers have become less popular because it is now possible to program digital computers to simulate moving physical systems. Normally, when working on paper, we count from 0 to 9, the decimal number system. Digital computers use a different system, known as the binary number system, to manipulate data. In the binary system, any number can be represented using only two symbols, 0 and 1. These symbols are used to represent the two voltage levels in a digital circuit. In the decimal numbering system, if a quantity larger than 9 is to be represented, then the symbols repeat by adding to the left of the first digit. Similarly, in the binary system, to represent a quantity greater than 1, the symbols systematically repeat by adding to the left of the first digit. In the decimal system, the least significant digit is on the right and the most significant digit on the left. The same applies in the binary system. In the binary system, each digit represents an increasing power of 2. The rightmost digit in binary number represents 2 to the power 0, or 1 in the decimal system. The next, 2 to the power 1, or decimal 2. The next, 2 to the power 2, or 4. The next, 2 to the power 3, or 8, and so on. A binary number can be converted to its decimal equivalent by adding together the decimal value of each of its digits. We will use this table to convert a binary number of 101 to decimal. The 1 on the right represents 1 times 2 to the power 0, or 1 times 1, which is 1. The 0 in the middle represents 0 times 2 to the power 1, or 0 times 2, which is 0. The 1 on the left indicates there is 1 times 2 to the power 2, or 1 times 4, which is decimal value 4. By adding the decimal value 1 derived from the binary 1 on the left to the 4 derived from the binary 1 on the right, we get decimal number 5. Therefore, binary number 101 equals decimal number 5. You can see that by using the table, it is easy to convert binary numbers into their decimal equivalents. You simply place the binary number under the table. Note the powers of 2 above the binary 1s and add them together. For larger numbers, the table can be extrapolated as necessary. The table can also be used to convert decimal numbers to binary. To use it to convert decimal 423 to binary, move along the decimal value row from the left until you reach the first number equal to or lower than the one to be converted. In this case, it will be 256. Write the binary digit 1 under this column. We now subtract 256 from 423, leaving 167. This is greater than the next decimal value of 128. So we add a 1 under that column. Subtracting 128 from 167 leaves 39. This is less than 64, so we place a 0 under this column. It is, however, greater than 32, so a 1 goes under the 6th column. Subtracting 32 from 39 leaves 7. 7 is less than 16 and 8, so zeros go under the 5th and 4th columns. It is greater than 4, so the 3rd column gets a 1. 7 minus 4 is 3, which is greater than 2, so a 1 goes under the 2nd column. 3 minus 2 is 1, so the 1st column gets a 1. Therefore, the binary equivalent of decimal 423 is 1101000111. Where large quantities of binary numbers must be manipulated, a programming technique known as octal notation may be used. Octal notation is comprised of a series of groups of 3 binary digits, known as triads. Since the largest decimal number that can be represented by 3 binary digits is 7, this is a base 8 system. To convert a series of octal groups to decimal numbers, each triad is first converted from binary to decimal, then the decimal number is multiplied by a power of 8, depending on its position in the series. The resulting decimal numbers are then added together. The conversion can be done using the table shown here. The triads are placed in the table as shown. Each group is then converted to its decimal equivalent. Each resulting decimal number is then multiplied by its relevant power of 8. Finally, the decimal numbers are added together to produce the decimal equivalent. Octal notation is often used for the transmission of data by aircraft computers and their peripherals. Another numbering system in common use in computer programming is the hexadecimal or hex system, which uses a base of 16. It uses the numbers 0 to 9 along with the letters A to F to make up the 16 required symbols. This table shows the relationship between hexadecimal, decimal and binary numbers. The primary use of hexadecimal notation is as a programmer-friendly representation of binary coded values, which may otherwise be unmanageably large. As you can see, 4 binary digits can be represented by a single hexadecimal digit. This means that a 16-bit binary code, for instance, can be represented by a 4-digit hexadecimal number. Digital electronic computers use digital data in the form of binary numbers to perform their operations. This form of data is represented by only 2 levels of voltage as opposed to the analog system's continuous variables. The 2 levels correspond to on or off in an electrical circuit. All data is represented and can be manipulated using just these 2 levels of voltage. In digital computers, binary 1 is usually represented by a positive voltage of typically +5 or +28 volts, and binary 0 by 0 volts or earth. This is known as positive logic. In a number of less commonly used systems, binary 1 is represented by a negative voltage and binary 0 by 0 volts. This is called negative logic. The term bit is used when referring to a binary digit. 1 bit is equal to 1 binary digit. If the system is using positive logic, a bit will either be a positive voltage to represent 1 or 0 volts to represent 0. A number of bits handled as a group are referred to as a byte. A byte typically contains 8 bits, but in some systems this number may be different. That is the end of the lesson. Here is a summary of the main points. An analog computer uses continuous physical variables such as voltage, pressure or mechanical movements to represent and manipulate the measurements it handles. Digital computers use the binary number system to manipulate data. In the binary system, any number can be represented using only two symbols, 0 and 1. A binary number can be converted to its decimal equivalent and vice versa using the table shown here. Octal notation is comprised of a series of groups of 3 binary digits known as triads. Since the largest decimal number that can be represented by 3 binary digits is 7, this is a base 8 system. The hexadecimal or hex numbering system uses a base of 16. It uses the numbers 0 to 9 along with the letters A to F to make up the 16 required symbols. Digital electronic computers use digital data in their operations, and this form of data has only 2 levels of voltage. The 2 levels correspond to on or off in an electrical circuit. The term bit is used when referring to a binary digit. 1 bit is equal to 1 binary digit. A number of bits handled as a group are referred to as a byte. The components that make up a digital computer system can be split into 2 groups, hardware and software. Computer software, or just software, is a general term used for digitally stored data such as programs of instructions read and written by computers. Hardware is the name given to the collection of mechanical, magnetic, electronic and electrical components making up a computer system. In this lesson, we will examine both hardware and software. And we will look at the regulations that are in place to ensure safety is not compromised when computers are used in aircraft systems. All computers have the basic hardware components shown in this diagram. This design is known as von Neumann architecture. It is named after its designer, the mathematician and early computer scientist John von Neumann. We will now describe each of the components in turn. The Central Processing Unit, or CPU, performs, organizes and controls all of the operations the computer can carry out. It is really the brain of the computer. The CPU consists of a number of individual components. The Arithmetic Logic Unit, or ALU, performs arithmetic calculations and logic operations using the binary number system. The shift registers are temporary stores. One of them, called the accumulator, contains the data actually being processed. The control unit contains the computer's clock. This is a crystal-controlled oscillator which generates timing pulses at a fixed frequency in order to synchronize the computer's operations. The CPU accepts digital signals from the input peripheral devices via its input port. In the case of a personal computer or PC, these may be the keyboard, the mouse, or any other input device. In an aircraft, the inputs could be from various sensors, radio altitude, barometric altitude, airspeed, fuel flow, and so on. After processing, the computer's output is fed out via its output port. In the case of a PC, the output peripheral may be a visual display unit, monitor, or printer. In an aircraft, the output may, for instance, be fed to an electronic flight instrument system or EFIS symbol generator, or to the flight management system control display unit. A computer needs a working memory to run the program of software it has to execute. To do this, a read-only memory or ROM device is used. ROM is programmed by the computer manufacturer. It cannot normally be altered by the user. It is usually contained on an electronic chip with no moving parts. Memory that retains data when the power is switched off is called non-volatile memory. ROM data is contained in non-volatile memory. Electronically alterable read-only memory, or EA-ROM, is a special type of ROM that can be electronically altered. This type of memory is used to hold the database of an aircraft's flight management system computer. The computer contains a worldwide database of all airfields, navigation aids, airways, and so on. Periodically, this data changes and the database needs to be updated. This is achieved on a 28-day cycle when a company, such as Jeppesen, contracted by the airline, issues an updated software program. This program is loaded into the FMS by a technician, overwriting the old data in the EA-ROM with the new. If a program has to be changed during operation, then the memory must be able to be written to as well as read. To do this, random access memory, or RAM, needs to be used as well as read-only memory. With this type of memory, data can be written in, read out, and altered at will. RAM is also required to store the data for processing, as this also will change continually. Memory that loses data in the event of a power failure or switch-off is called volatile memory. RAM is normally volatile memory, so any data stored in it is lost in the event that the power is removed. Buses or bus bars are used to connect the CPU to the computer's memory and to the peripheral equipment. A control bus is used by CPUs for communicating with other devices within the computer and with peripheral devices. The control bus carries commands from the CPU and returns status signals from the devices, while the address bus carries the information on which device the CPU is communicating with, and the data bus carries the actual data being processed. Digital computers use digital or binary information, but many aircraft sensors produce analog information in the form of varying voltages, pressures, temperatures, and so on. A component known as an analog to digital or A to D converter is required to allow the computer to read this data. When a digital computer has to pass information to an analog device, the process is reversed and a digital to analog or D to A converter is used. One computer which uses such a system is the central air data computer. This computer takes in static and dynamic air pressure and outside air temperature signals and produces outputs for instruments such as the Mach meter and the true airspeed indicator. In computing, multitasking is a method by which multiple tasks share common processing resources. In the case of a computer with a single CPU, the CPU can only actively execute instructions for one task at a time. Multitasking solves this problem by scheduling which task may be the one running at any given time, and when another waiting task gets a turn. The act of reassigning a CPU from one task to another one is called a context switch. When context switches occur frequently enough, the illusion of parallelism or of actions happening simultaneously is achieved. Multiprocessing is the use of two or more central processing units or CPUs within a single computer system. This type of computer can genuinely complete a number of tasks simultaneously. An operating system, or OS, is a set of system software running on a computer that manages the system hardware and controls the execution of application software. You will no doubt have heard of the Microsoft Windows operating system used on many personal computers. An example of an operating system used in aircraft computer systems is the Lynx operating system, supplied by the Linux Works Corporation, which is used in the Airbus Air Traffic Services Unit, ATSU, computer. This computer integrates all services dedicated to data communication between the aircraft and the air traffic centres, as well as the Aircraft Communication Addressing and Reporting System, or ACARS, functions. Permanent storage for computer programs and the work they generate is provided by storage peripherals. These can take the form of magnetic disks, optical disks, or solid-state electronic chip devices. The storage capacity of these devices is measured in units of bytes, normally megabytes or gigabytes. 1 megabyte is approximately 1 million bytes, and 1 gigabyte approximately 1,000 million bytes. There are two types of magnetic disk systems in common use. Hard disk drives are usually magnetic disk drives, with the disk being an integral, non-removable part of the unit. Floppy disks are also magnetic disks. These and optical disks, such as compact disks or CDs, and digital versatile disks or DVDs, can be inserted and removed from drives, making the data they contain transportable and securable. Data can also be held on solid-state electronic chip devices using a method known as flash memory. Again, these devices can be removed from the computer. A programming language is a language used by a computer programmer to write computer programs. There are a number of languages in use. Here we will define three of the most common types. Assembly languages use a symbolic representation of the binary codes and other constants needed to program a particular central processing unit. This representation is usually defined by the CPU manufacturer and is based on abbreviations, called mnemonics, that help the programmer remember individual instructions. A particular assembly language is thus specific to its related CPU. A high-level programming language is a programming language with strong abstraction from the details of the computer. Many normal words are used during programming. In comparison to assembly language, it is easier for the programmer to use and is more portable across different types of computer. A scripting language is a programming language that allows control of one or more software applications. Scripts are distinct from the core code of the application, as they are usually written in a different language and are often created or at least modified by the end user. Aircraft systems which are computer controlled include the Flight Management System, FMS, the Digital Flight Guidance System, DFGS, the Ground Proximity Warning System, GPWS, the Traffic Alert Collision Avoidance System, TCAS, and an increasing number of other systems. Operation of these systems is explained in the relevant lesson. Current design favours the use of a dedicated computer for each separate system. In the future, however, we may see sharing of computer power in the form of an Integrated Hazard Warning System, IHWS. Here, a powerful central processor with appropriate backup handles inputs from the stall warning system, wind shear detection, GPWS, TCAS and the weather radar, processes the information and prioritizes warnings to the crew. Fly-by-wire aircraft take computer control very much further, when the whole flight envelope is controlled by computer processors with inputs from the crew when necessary. Where computers are used to control safety-critical pieces of aircraft equipment, it is essential that the software is exhaustively tested to ensure that there are no bugs in it, which could lead to failure of the equipment. The regulations governing this testing and the acceptable failure rates of software are contained in the document EuroCAE ED12B, titled Software Considerations in Airborne Systems and Equipment Certification, issued by the European Organisation for Civil Aviation Equipment. That is the end of the lesson. Here is a summary of the main points. Computer software is a general term used for digitally stored data, such as programs of instructions read from and written to by computers. Hardware is the name given to the collection of mechanical, magnetic, electronic and electrical components making up a computer system. A basic digital computer consists of a number of components joined together in a design known as von Neumann architecture. The Central Processing Unit, or CPU, performs, organizes and controls all the operations the computer can carry out. Within the CPU, the Arithmetic Logic Unit, or ALU, performs arithmetic calculations and logic operations using the binary number system. The shift registers are temporary stores of data, and the control unit contains the computer's clock. Computer memory that retains data when the power is switched off is called non-volatile memory. Memory that loses data in the event of a power failure or switch off is called volatile memory. Read-only memory, or ROM, is non-volatile memory. Electronically alterable read-only memory, or EAROM, is a special type of non-volatile ROM that can be electronically altered. Random access memory, or RAM, is normally volatile memory. Buses, or busbars, are used to connect the CPU to the computer's memory and to the peripheral equipment. A component known as an analog to digital or A to D converter is required to allow the computer to read analog data. A digital to analog or D to A converter is used to pass a computer's output to an analog device. Multitasking is a method by which multiple tasks share common processing resources. Multiprocessing is the use of two or more CPUs within a single computer system. An operating system, or OS, is a set of system software that manages the system hardware and controls the execution of application software. Permanent storage for computer programs and the work they generate can take the form of magnetic disks, optical disks, or solid-state electronic chip devices. A programming language is a language used to write computer programs. Assembly languages use a symbolic representation of the binary codes and other constants needed to program a particular CPU. A high-level programming language is a language with strong abstraction from the details of the computer. A scripting language allows control of one or more software applications. Aircraft systems which are computer-controlled include the Flight Management System, FMS, the Digital Flight Guidance System, DFGS, the Ground Proximity Warning System, GPWS, the Traffic Alert Collision Avoidance System, TCAS, and an increasing number of other systems. The regulations governing the testing and the acceptable failure rates of computer software used in aeroplanes are contained in the document EuroCAE ED12B, titled Software Considerations in Airborne Systems and Equipment Certification, issued by the European Organisation for Civil Aviation Equipment.